So, everyone's working hard on their form. It's hard. Lots of work to be done. So I'll have my office hours starting in my office. People show up, move to a bigger room if necessary at 3 o'clock. Okay. All right, so let's remind ourselves where we were. So we're talking about the problem of driving quantum coherence. And, we've been talking for many lectures now because it's such a fundamental and important problem of the idea of how we can think about driving quantum coherence, quantum superposition between two quantum states as the problem of Laura precession of spin on the Bloch sphere. And so as we've discussed now many times, there are many different ways we think about that with many different representations. And we need to kind of be able to speak many languages and go back and forth between these different ways of expressing the same thing, because those different ways of expressing it can sometimes, each of those languages can be useful in different contexts. Okay? So, for example, we have what are called the Bloch equations, which is just the equation of the gyroscope, which is looked at in terms of the x, y, and z, components of the Bloch vector are the differential equations that are written here. Okay? And those components of the Bloch vector are related to the components of the density matrix in this particular way. So, for example, the z component of the Bloch vector, which we call W, is the population difference between spin up and spin down. Whereas the off-diagonal elements are related, the real and imaginary parts of the coherence represent the x and y components of the Bloch vector, right? Because they lie in the equator of the Bloch sphere. And the equator of the Bloch sphere tells me something about quantum coherence, right? Okay, so for what we're focusing on, and we will for many lectures to come, this semester and next, we're looking at the problem of an atom interacting with typically a laser, but it could be a microwave. It depends what this energy difference is. It could be a UV laser. Who knows? Maybe someone had one of them in their lab. It's kind of, you never know. And the point here is that there's some two levels by which I tune my laser near to resonance. And in this, I'm looking at a specific example here of thinking about these two energy levels associated with an S state and a P state, where there's a loud electric dipole transition between these two levels with linearly polarized light. Those details, the polarization, all that, is not so important to focus on at the moment. The point is that there's two levels and they're connected by my interaction Hamiltonian, which we're taking to be an electric dipole interaction. Okay? So this is the electric dipole operator, and this is the electric field associated with the laser, which we treat as a classical field. Okay? And it's oscillating at the laser frequency near to resonance. And as we discussed, so now we're close to resonance, we can restrict our attention solely to this two-dimensional Hilbert space associated with these two levels, in which case the Hamiltonian for the system takes this form involving the energy levels of the atom, which are eigenstate. These are eigenstates of the atom. And then we have the interaction Hamiltonian, the dipole interaction, which is not diagonal in that it has off-diagonal elements in that basis. Okay? And this is the dipole matrix element, which I'm taking to be real, which I can do from some choice of the phase of the wave functions. Okay. So importantly, we now, once we have a two-level system, we can now think about this as a qubit or a pseudospin. Yes, sir.
I have a question about the convention of the 2D vectors. On the one hand, the 1,1 element is spin up, and the 2,2 element is spin down. Like in the convention where sigma z. But on the other hand, the ground state is spin down.
Not necessarily.
You follow?
I hear what you're saying, but the ground state isn't. First I say, one has to be very careful about the physics versus a mathematical mapping. Okay? So I specifically set it up in the problem I think I thought about, just as for a physical example, as an electron in a magnetic field. A true honest-to-God electron with true honest-to-God spin in a true honest-to-God magnetic field. So if I say the magnetic field is here, well, in this case, the ground state, you're right, is aligned with that, is spin up, right? Because that's the lowest energy state. I'm sorry. Yeah, that's the lowest energy state when the spin is aligned with the magnetic field. And the magnetic, right? However, so that's when the magnetic moment is aligned with the magnetic field. But for an electron, it's the opposite, right? So the actual ground state is spin down.
Right.
Okay? But don't confuse yourself about this. Do not be fixated about this, because this is the wrong thing to be thinking about. It's just a mapping where I'm just going to say there is a pseudo field. It's not the actual magnetic field, but I'm just going to call the ground state spin down and the excited state spin up in some pseudo-magnetic field, which actually is the problem of an electron in a true magnetic field, but I don't care, and nor should you, any of you, because that's not the point. The point is the mathematical mapping, where I'm just going to say, for my two-level atom, this is the ground state and this is the excited state. And I will think about this as equivalent to a mathematical problem of an electron in a magnetic field. Yeah.
Spin W is representing the population of upper and lower state electronic system also? Like if you write the density matrix or pseudo.
That's right.
Okay.
So sigma z, so remember that W is the expected value of sigma z, right? Sigma z is always has eigenvalues. This is the sigma z operator, right? So if I look at the expectation value of this, what's that? It's the difference in the population up minus the population down. Now what you call up and what you call down is your choice. In a mapping of two energy levels or two states of a two-dimensional Hilbert space onto a qubit. The convention we always take in thinking in quantum optics is the upper state to be spin up and the lower state to be spin down. And that is equivalent to the problem of an honest-to-God electron in an honest-to-God magnetic field. Good. So, yeah. Okay, so, right. So this is our mapping. And that should not be a plus. That's a minus. So, with that mapping, then the Hamiltonian can be thought of as any two-level system can be thought of as the dynamics of a pseudospin in a pseudomagnetic field. Okay? And when we go to the rotating frame and make the rotating wave approximation, then neglecting any constant term, our Hamiltonian for our two-level atom takes this form, where the detuning is, as always, the difference between the applied frequency and the resonance frequency. And the Rabi frequency, now instead of being set by the energy, the actual Rabi frequency, which determines the rate of interaction, is determined by the energy scale associated with the electric dipole. Okay? So in a true magnetic dipole moment interacting with the true magnetic field, like the spin electron, this would have been mu dot B, right? But here it's E dot E, which is an energy, right? And then there's a frequency associated with that. The minus sign is again a convention we take because we're talking about this thing is going to be positive because the electron charge is negative, right? So the dipole moment will be negative and that takes care of it. Matt, you got a question?
Yeah, so just to be clear, when you were talking about microwave stuff earlier,
Yeah.
that would have been a real magnetic field.
That's a different deal. So if I have, for example, if I'm connecting two levels, say, that are separated by some microwave frequency, like 9.2 gigahertz in the ground state of electronic ground state, but it's the hyperfine, then that's the true magnetic field. But if I'm way up, high up in principal quantum number, where the energy differences are very, very small, those energy differences can also be on the order of microwaves, and that's the electric field. That's an electric dipole. So there's actual physics underneath that, thinking about the actual interaction is. But for the moment, we're just focusing on thinking about this as something like an optical frequency near an optical electric dipole allowed transition. But one has to think specifically about the energy levels, and there's underlying atomic physics about what is an allowed transition, what is the kind of interaction that couples. Okay, good. So, the point here is that this problem of thinking about a coherent laser or optical field coupling these two levels is equivalent to the problem of Rabi oscillations that we studied for a true spin. But this is now a pseudo-spin, right? And so, for example, if we're right on resonance and we say the phase, we choose the phase at the position of the atom to be 0 at time t equals 0, then we get this kind of rotation of the block vector around the block sphere, which would periodically give me go from ground to excited and back to ground. Intermediately, I'm in a coherent superposition of ground and excited states. And if I made the laser intensity exactly right, and thus the amplitude of the field such that this is some well-defined frequency, typically I have a milliwatt per square centimeter. This is about a few megahertz, just for those of you who care about numbers. Then, in a few microseconds, I would do these kinds of oscillations. Okay. All right. And now, one of the things we're going to talk about in the next few lectures is the relationship of this problem to the problem we studied early in the semester of the Lorentz oscillator, of a charge on a spring. How is this different? How is this the same? In what sense can I think about them equivalently? We'll come back to that probably on Wednesday. But just briefly, what we showed last time, that this was equal to if I thought about this as a, what is the electric dipole of this atom doing as a function of time? I start out with the atom in the ground state. It's got a symmetric distribution of electron cloud around the nucleus. It has no dipole moment. But as I force it with the electric field, I induce a dipole moment. And that dipole moment will oscillate. It will oscillate with it like this. It's not exactly going to be monochromatic because these amplitudes are changing with time because the u and v components of the Bloch vector are changing with time, right? They're changing with the Rabi frequency. So that's already a little bit different from the charge on a spring. This is actually a nonlinear oscillator. It's not a linear, it's not a Lorentz oscillator at this stage. I'll come back to that. Right? Because these guys are oscillating at the Rabi frequency, and they have this like amplitude modulation at the Rabi frequency. All right. Very good. Yes, I'm listening.
So U and V are related like the two components of a circle, right?
They are.
So shouldn't this look like an ellipse?
Well, the dipole, I'm not sure why it's not oscillating in the equator, right? This is just what the U and V components do as a function of time. Now, I could think about what this vector looks like in the equator and what that trajectory is in this case. But I'm not sure that's going to give you any particular insight into what's going on. Really, it's what's going on in the sphere that matters. All right. Very good. Now, I want to come back to a point that Matt raised in the last lecture about the issue that I have completely ignored the fact at this stage that actually the excited state is not a stable eigenstate of the system. It's a metastable state. It has a finite lifetime, and the system will spontaneously decay. And that's a complicated story. A story that we're going to unfold at we're going to peel off different layers of the onion of that over the course of this year. One of the things that we see about such a kind of evolution is, let's say I turned off the laser. Okay. So let's say I could do this hybrid Q-pulse really quickly compared to the time it takes for the atom to spontaneously emit. Let's just imagine I had so much good intensity I could do that, right? So I put the atom in the superposition of these two states. What's going to happen? Now I turn off the laser. Yeah.
Eventually it'll decay back down.
It'll all end up in the ground state. Right? And if I did a pi pulse, a very quick pi pulse, and I put it up there, what's going to happen? It's all going to end up in the ground state. And so in some sense, I lose any memory of what the state was. It goes to the ground state, irrespective of what superposition I had. And thus we see one aspect of this kind of evolution is that it is irreversible. It's not time reversal invariant. I can't go backwards in time. And that's already weird because, of course, the Schrödinger equation is time reversal invariant, meaning it evolves according to a unitary transformation. If I want to just go back, I just hit U dagger on it and I go back to where I started. And so obviously that is not evolution according to the Schrödinger equation. Huh? Doesn't everything evolve according to the Schrödinger equation? Well, like I said, that's a pretty complicated story and one that we will discuss over the course of the academic year. But we have a similar story in thinking about our Lorentz oscillator, right? When we write down our Lorentz oscillator, we said we had a charge on a spring, and the spring had a hook force, a restoring force. And then we just put in friction. We put in gamma as a damping of the oscillator. But of course, the Newton's equations or Hamilton's equations, or whichever classical mechanic you like to associate your equations with, are time reversal invariant as well. So the fact that we have damping in our Lorentz oscillator is a phenomenological, right? We're not by first principles saying where the damping comes from. We're just put in a friction coefficient or a damping coefficient. Obviously there is microscopics underneath that from which that forms, and similarly in quantum mechanics. And we're going to unfold that. So what we're going to talk about today is a phenomenological description and this phenomenological language survives till today. We use the same kind of jargon. I'll explain that in a moment. So we come back to this thinking about our Rabi oscillations. If, as we said, we start with the Bloch vector, say, at the South Pole, for example. And if we drive the system on resonance with a particular phase, then the system, as we just described, will undergo the Bloch vector will undergo Rabi oscillations, and those are perfectly reversible. After a certain amount of time, I got here, I could just go back to where I started. But we can say, well, phenomenologically, we're going to say there's some kind of damping which would take the system, say, from the excited state to the ground state with some damping rate, or some time constant. And the time constant which decays the populations is known as T1. All right? So one talks about the T1 time as to say that this is what's sometimes known as longitudinal damping of the Bloch vector. So there's some rate of decay, 1 over T1. We think about it as an exponential decay. In the same way that we think about a charge on a spring, the amplitude of the charge decaying exponentially some rate. Now, there's a different kind of mechanism. We'll talk about this today, which could say, instead, remember, if I start with a superposition, I can also, in principle, lose coherence without changing the population. And that can happen because I can mess up somehow the phase relationship between the spin up and spin down components, or excited and ground state components, without affecting. Now, if I affect this, I can also affect, if I affect the population, I can also affect the coherences. But as we will see in a moment, there are situations where I might affect the coherences without affecting the populations. And that kind of decay, which takes me back, this is what's known as transverse decay. Transverse in the sense of the block vector. That is known as the T2 time. And there's a rate of decay, 1 over dt2. Okay. So if I have the driven system where I put on a torque vector, which in the absence of decay would just cause precession of the block vector, there's going to be a damping. And generally I'll have some kind of spiraling in of the block vector to the interior of the block ball. So whereas in the absence of damping, I stayed on the surface of the block sphere and remained a pure state, in the presence of the damping, the description is now one that involves mixed states. Yes, Sam?
Why does the T1 time bring you to the center of the block sphere? Wouldn't it, I mean, it leaves you in long enough time, you're in a pure state, you're pointing down, right?
This, if I had just T1,
Yeah, just T1.
then, well, okay, so then what I would do is just go straight down.
Okay.
T2 brings me in, but now I'm having the combination of 3 effects. I'm having, firstly, I have my torque vector out of the board, omega, which in the absence of any damping would just make me wildly oscillate. I have T1 and T2 going on. The T1 takes me straight down, and the T2 takes me in. And eventually I'll have 0 coherence. And I might have some population because I'm driving the system in steady state. So maybe I don't understand your question, so maybe you can ask it again.
I just thought, like, if you wait long enough near the T1 time, you're gonna end up in the ground state, right? So
If
you
I
end up
do
in
without the
pure
laser on,
state. With the laser on.
yes,
Okay.
that's the difference.
Okay.
So there's a steady state, there's a detailed balance here, because the laser is trying to push population into the excited state. The spontaneous emission or whatever is trying to push it to the ground state, and there's some detailed balance between them.
Okay.
Yep, yep.
What was the physical intuition again for why we get the dephasing, the T2?
Well, I haven't given you much where that comes from. I'm going to talk about that now. I'm saying we can imagine there will be some effects, and we'll talk about some of them. So, a few things that we learned from this kind of picture is that, firstly, we're going to be talking about irreversible behavior. And secondly, we have mixed states. So there's an intimate relationship here between including damping in quantum mechanics and generalizing our description beyond pure states to include mixed states. Now we're going to get, there's so many subtleties in this, and we'll get to them, how maybe sometimes we can get away with thinking about pure states even though we have damping. We'll come to that. There's various levels of subtlety here. All right, so the first thing we're going to do is just write down some phenomenological equations, okay? So if I was a good professor, I would have left those equations up here, the block equations, because I'm going to write them down again. Right. So the point here is that we're going to, the block equations now are going to, we're just going to say, well, there's a phenomenological damping, right? So the transverse components damp to zero phenomenologically. I'm not saying where this comes from. I'm just saying there's a damping of this thing to zero. Okay, let me just finish writing these down. And then the inversion is going to have a decay at the T1, and it, we're going to say, goes to some steady state. And that steady state, in this particular case, depends on the intensity of the laser. So these equations are phenomenological equations that are, in fact, ones that we can derive from first principles pretty exact, you know, with good approximation, that well describe a qubit being driven with some Rabi frequency and some detuning and some decay terms T1 and T2. Yes, someone had a question.
So actually, what I understand from damping or this lifetime is that the energy of the system should have some imaginary part.
We'll get there. At this point, I haven't actually, we'll come back to that. Hold that question, it's a very good question. At this stage, you know, we're going to connect various threads of thought and ways of thinking about the same thing. Again, there's just many different ways of representing the same physics in different mathematical ways. This is one way, which just says, I'm going to say that the transverse components of the block vector decay at the rate 1 over d2, and the longitudinal component of the block vector decays with exponentially with the rate t1, but the longitudinal component goes to steady state. So in the absence of driving, then this thing in steady state, W would equal this in steady state. Okay. All right. So these are known as the Bloch equations. These are the equations that Bloch wrote down. I think I wasn't around, but and I think Bloch introduced these terms T1 and T2, and they survived to today. People always talk about the T1 and T2 times about their qubits. All right. Right. Okay. So now let's talk a little bit more about some of more of the intuition that we were talking about where these things come from. So, one way we get these damping terms. So I'm talking here about physical mechanisms for damping. Okay. So one physical mechanism can be finite lifetime, meaning that a system prepared in some state doesn't live forever in that state. It will decay out of that state to some other state. That we call finite lifetime. Okay, so phenomenologically, let's see, I might have some population in some state. Okay, which we know is the diagonal matrix element. This is the population of that state. If there's no other driving on the system, then if this thing decays, then this population as a function of time will decay with some rate. Where T sub alpha is the lifetime, that's the jargon we use of the state alpha. So the population decays in this way. Okay? If this were a pure state, then this would say that this now this is not really fair, because I just said that if it's decaying, it's not a pure state, right? It might start as a pure state, but if it goes on this trajectory through the center of the Bloch sphere, intermediately, it ain't a pure state, right? So that's really not correct. What I really should say is something like this. This is the average over the ensemble in an ensemble decomposition. As we said, you can always write this with a statistical mixture of pure states. Then I can get something like this. Okay. However, I want to address just quickly here, you kind of see, sneaking in here, we'll come back to this, that maybe this has something to do with an imaginary part of an energy, because if I had something that, because if I look at this kind of loosely, what's going on is that the magnitude of this thing is kind of like, in some very loose way, and we'll come back to this, something which is decaying like this, right? If I square, I mean, totally loose with the mathematics here. You know, this was the average over the ensemble here. It's not the average. I took the square root inside. What the heck am I doing? But this is just a little bit, nothing up my sleeves. I'm not wearing sleeves today. To say something about, we know if I had just Hamiltonian evolution, probability amplitudes would typically oscillate like e to the minus I omega t. If we're having something that like decays like that, that's like having an imaginary part to the energy. I'll come back to that.
Yeah. What's the relationship between the subscript I and the subscript alpha?
Nothing. I here is just to say I can always write the density matrix as we described as some statistical mixture of pure states, right? As we know. I is just a label of saying I have many, some number of pure states in the statistical mixture.
Okay.
Alpha is just some particular state that I'm looking at. So,
But alpha runs from 1 to 2.
it could. I could. In this case, yes. It depends how many levels I'm keeping in my quantum system, but right now, yes, alpha runs from 1 to 2.
Okay, so this is more general than
This is a little bit, I'm saying things a little bit more general than the two-level system, but we can restrict ourselves to that. All right, so So for example, if we go back, to, as Dave said, if we think about our two-level atom, where alpha is E or G, right? Then we would say in the absent and driving, the excited state would decay with some rate of decay of the, where this is the lifetime of the, 1 over the lifetime of the excited state, and the ground state would, well, it would increase. So this is the total, the two-level system, right? And then the difference between these decays at the rate of the excited state, which tells me that the T1 time is related to the lifetime of the atom, which is 1 over the lifetime of the atom. Right? Okay, however, things get more complicated when I think about the off-diagonal elements. Let's just think for some arbitrary off-diagonal element. In this case, it would be for the two-level system, E and G. Right? Well, if this were a pure state, then this would be that. Right? So let me do the same kind of trick that I did here. I said, let me have an ensemble of possible states, and I'm going to sum over them, just like I did over here. Okay? I'm sorry for my sloppy handwriting. Let me clean it up. So the I here labels the member of the ensemble. So this is equal to the following. Let us assume, for simplicity, that every member of the ensemble here, all right, I'll just write it out. Hang on. You might sleight of hand here. So what I've written is each probability amplitude has a magnitude and a phase. Okay, so this is the phase of this complex number written in polar decomposition, and this is the phase of this guy, right? Now here I'm just going to be a little bit loose here. Let's say I want to see the effects. There's two different effects that can lead to decay of the off-diagonal elements of the density matrix. One is decay of the amplitude, and the other has something to do with the phase. Okay? So what I see here, I could just sort of say loosely, well, there's this guy's, they decay exponentially with a rate that was half the rate of the population because it was the square root of this. And then I have something that depends on the phase difference between the two. Okay? So, to emphasize, we have two different ways that can affect the decay of the off-diagonal elements. One is the decay of the amplitudes. So finite lifetime of alpha or beta or both will lead to decay of the off-diagonal elements. But there can be another effect, which could be that there are random phases. For example, a problem you all loved for homework was the problem of the colliding atoms, or the colliding Lorentz oscillators, right? Where you could get a kick that gave a phase difference between, in the coherence. And that, if I have some kind of random phase here, for example, if I have a gas that is sufficiently dense and I can have collisions, those collisions can cause the phase difference to change without changing the population. And that will also, if that phase is random, can also lead to a decay of the off-diagonal elements, because the off-diagonal elements depend critically not only on the amplitude, but on the delicate phase relationship between the two. And if that delicate phase relationship is damaged due to some external perturbation in a random way that I can't keep track of, then that's going to statistically average. And so this, as we saw in our homework, and there is method to my madness, these homeworks do connect, ultimately, they will all connect to homework. There'll be an additional decay, which I'll call here beta. Oh God. There, beta alpha sub beta. It's called beta in the homework, that's crappy. What did I actually do? Yeah, that's what I did, so we'll read it that way. The point being the following. The T2 time of the system depends on two things. It depends on the lifetime of the two states over 2. And something having to do with dephasing. So, yes, sir, you have a question?
Does it mean that in your model, your two-level atom is not isolated?
Say again the question.
So your two-level atom in this model is not isolated, it's embedded in some kind of medium.
Well, it absolutely has to be, for any of these damping effects to occur, my two-level system cannot be completely isolated from all other degrees of freedom. Because if it were, the excited state would be an eigenstate. And if it's an eigenstate of the system, it's a stationary state. Now, what are the different kinds of perturbations or environmental effects that could affect the system? Well, I could be, it's embedded in a matrix, like, you know, I have an embedded atom that's inside a solid state matrix. It might be all the phonons in there that are causing something. Or it might be that I don't have just one atom, but I have a whole gas of atoms. And one atom is seeing the effect of all the other atoms around it, and those other atoms can collide with it. But even if I have one single atom in the vacuum at 0 temperature with no other seeming interactions, there's always the quantum mechanical fluctuations of the electromagnetic field. And that fundamentally is always going to give me some decay, as we will see. Okay. An important point, though, that I want to emphasize here is that typically, T2 is much, much smaller than T1. Because typically this is going to be big compared to this. Not always true, but in most systems that's true. For the reason being is that physically there's a much lower barrier to something which affects the relative energy and thus the relative phase. Because remember, energy phase in the wave function is accumulated depending on the energy, right? The phase in the isolated system is that, right? Because I have an e to the I e over h bar t, or minus that, right? So if the energy fluctuates somehow, that's going to give me a fluctuation in phase. So if I have, for example, an energy level that has some magnetic dipole moment, if it's sitting out here in my 60 hertz world, there's going to be some fluctuation just through the ambient, magnetic fields that's going to make that energy level fluctuate a little bit. In the context of collisions that are elastic collisions, meaning to say that they just give me some change in the energy of the two-atom wave function and then that, without actually causing population to go, is another way I can get a phase accumulation. So it's typically the case that T2 times are very small compared to the T1 times. They're the things that limit things. Now in an optical two-level atom, it's not true, it's the opposite. It's really, if I have an atom and it's sitting, I have one atom and it's just sitting there, there's really, and I've isolated it from all fields and I've made its magnetic dipole moment 0, I've chosen the clock states, then I can forget about all this stuff and just have lifetime. We have to think about what's going on. Yeah?
So theoretically, T2 has to be less than or equal to T1, right?
No, it doesn't have to be. Let's look at the extreme case. Let's suppose that beta is 0. So let's look at my two-level atom. Then T1 is equal to 1 over the lifetime of the excited state, right? What's T2? Well, it depends. It depends upon whether the ground state also decays, but typically the ground state we would take to be the actual ground state, which doesn't decay. And in the absence of any background, if I completely isolated all the background, and the only thing I had was the electromagnetic vacuum, then what is T2? So it's actually longer than T1 for this case.
So do the diagonal, off-diagonal terms decay as e power minus t by T2?
That's correct.
And the off-diagonal element,
The off-diagonal elements will decay as T over T2.
and the diagonal elements change from each other
And
and
the
redistribute with T1.
with T1, yeah. And this decays, in this case, with half the rate. That's not typical. It's not typical, but we would try pretty hard in an engineered quantum system to make this true. Okay? Because typically, this stuff is going to dominate. And it's very hard to get rid of this. But if we could, we would have a longer coherence than T1. But that's atypical. All right, very good. All right. There's one other aspect of this which you're looking at in your homework, which is known as inhomogeneous project. So this is really more about something I would say is more related to classical uncertainty of parameters. What do I mean by that? Well, let's take a specific example. Let's say I have a gas of atoms. Okay? And I'm going to shine a laser beam on these atoms. But my laser beam is focused in some way. And the laser beam is propagating primarily in this way. It has to say its peak intensity on this axis, but there's some distribution of intensity as a function of this axis, the transverse direction. So that's the intensity of my beam. It is not uniform over the distribution of atoms. The atoms in the center see a slightly higher intensity than the atoms off axis, right? What does that mean in terms of driving Rabi oscillations? Well, what it means is that the electric field at each atom is going to be slightly different, which means that there's going to be a distribution of Rabi frequencies at different positions on this axis, right? The Rabi frequency is not going to be the same. Some will be higher and some will be lower. So if I were to look at, measure the population in the excited state, not by measuring any one atom, but by measuring all atoms at the same time in some measurement, which would average over the ensemble of the atoms, which is typically how you do it. You don't just look at that atom. Sometimes you do, but mostly you don't. Then you have to average the Rabi oscillations over the distribution of the probability of the atom sitting at a particular x. Now, of course, that would depend on the distribution of intensity and the distribution of positions, depending on the gas and how it's distributed. And so what that would mean is that my Rabi oscillations are not going to be the Rabi oscillations of any one atom, but they're going to be the average, the statistical average of all those. It's a statistical mixture. And what's that going to do to my Rabi oscillations? So if I forget about the lifetime, let's say, well, you know, after some lifetime, of course it's going to decay, but let's just say, so these are my Rabi oscillations for some particular Rabi frequency. But now I have some that are slightly higher. Well, that's a lot higher. And some that are lower. And so what's going to happen, depending on the range of these things, they're going to get out of phase with one another. And so what's going to happen is I'm going to get some kind of damped oscillations here that have nothing to do with the fact that the atom spontaneously emits, or is colliding, or is having is being perturbed by an external force. It's due solely to the fact that I didn't know what the intensity was where the atom was, and I had a lot of atoms. Or in shot to shot to shot, if I have one atom, if I have a different intensity, that's morally equivalent. And that is what's known as inhomogeneous broadening. Why is it called broadening? Well, that's a, yeah.
Can you get this if you have, say, like a trapped atom in
Yeah.
some harmonic potential, and then your field is inhomogeneous over that?
Yeah, so the atom is moving. Say it started here, but it's in a track and it's oscillating around. That's also going to give you inhomogeneous broadening. Absolutely. And so what we talk about then is that the this effect gives me an effective dephasing of the system. Yes?
Would this effect be happening in both the cases where you have the vertical magnetic field having a spread, one that's supposed to be DC, as well as the one that
Sure,
is?
absolutely. So I can have a spread in the detunings. Here I just talked about a spread in the Rabi frequency. A spread in the detunings will also give this effect, and that spread of detunings can be due to a spread in the resonance frequencies for a fixed oscillation. That's like the problem you have in homework. So one talks about T2 star. That is also an ancient piece of Sanskrit, but it's still used today when one talks about the dephasing time of my qubit. So T2 star includes inhomogeneous broadening. The term broadening has to do with spectroscopy and whether your line that you see in your spectrum is broad or narrow, and that's inversely related to the rate of decay. So that's why it's called broadening. So the rate of decay of the coherences is 1 over T2 star, which is, anyway, that includes the broadening. Okay. Yes.
So just to be clear, is this a more general like class of decoherence? Like would Doppler broadening be considered like a form of inhomogeneous broadening?
Well, yes. I mean, motion. If I have a uncertain speed of the atom, that gives me an uncertain detuning, and the uncertain detuning gives me a form of inhomogeneous broadening. If I were to look at Rabi oscillations in a thermal gas, because they would see different detunings, the Rabi oscillations would mess up in that way. However, I want to be very careful of the word that you use, decoherence. So that's a tricky business. We're going to talk about. You've seen that some of it in your homework. This effect, unlike spontaneous emission, is not irreversible. It is not. As you're seeing in your homework, it's perfectly reversible. Because this is not due to any, it's just the fact, it's not due to any information being leaked to the environment that we lose. All of these oscillations are perfectly coherent to the degree to which there's no lifetime or anything else. And so, in principle, we can reverse this effect, as we will talk about now.
Even if we do like echoes and things, we'll end up losing it, right?
We're going to talk about it. So, an important thing that you're looking at your homework, and I wanted to get you here wanted to talk about some of the things you're looking at in your homework. Here, so that we make sure we're on the same page. So the first question is about measuring the decay of quantum coherence. So, when we want to measure something about coherence, how much coherence there is in a physical system, we go back and think about the fundamental way we think about coherence is to think about an interferometer. So, optically, if I want to think about temporal coherence, how long is an oscillating electromagnetic field have a well-defined phase before it loses that phase memory? What I would do is make an interferometer. We like to draw this kind of two-path interferometer because it's easier to draw even if it's not easy to align in the lab. The Mach-Zehnder interferometer. Where we think about two paths where I can move this mirror around in something or other so that I can affect the path difference between these two paths, right? And for a monochromatic field, as we've seen before, what I'll see is coming out this path, I'll have some fringe, depending on the path difference, and then I'll have like a minus sign in this guy, coming out of that fringe, right? This is for a monochromatic field. But if I have some distribution, with some probability distribution of frequencies, some spectral distribution, then that can dephase this. And depending on the spread of frequencies, with the delta function, I just get the one fringe. But if I have the spreading frequencies, then I'm going to get my interferometer will look something like, I'll see the intensity fringe decay, right? And that decay will be related to the coherence time, which would be 1 over the spread in frequencies. So the way that I measure coherence is I look at interference between those two alternatives. If I can see interference between them, then I say they were coherent. If I don't see that interference, then I lost my coherence. So I want to measure the coherence in a quantum position. And what I claim and what you're studying in your homework is that is just isomorphic to a two-path interferometer. I can create effectively a two-path interferometer in my two-level system that I can think about as two paths that I put on a beam splitter and interfere them with one another. And that is what we call, for the two-level system, the Ramsey, what is called the Ramsey interferometer. So in your homework, you're showing the mathematical isomorphism between the Ramsey interferometer and the Mach-Zehnder interferometer. That's the context you should think about this. This is sometimes known as an SU2 interferometer. So any two-level system is like two-level system with complex amplitudes is like the dynamics on the Bloch sphere. So my Mach-Z interferometer has a mapping onto the Bloch sphere. Let's talk about it. So let's say that my random interferometer, I'm going to have the following situation. I'm going to put on a pi over 2 pulse. Doesn't matter what axis in the equator I do it. Let's say I do it along the x, and then I wait a time t, and I do it again. So I'm going to think about these two paths of the interferometer as one being associated with one state, let's call it G, and the other associated with another state. Again, this is a mathematical mapping. I'm associated two different quantum states with these two different paths. Okay, so I start the system in the ground state, entering my interferometer. Now, I'm going to put on this pi over 2 pulse. And my pi over 2 pulse is going to have some detuning. That's not equal to 0. But I'm going to choose the Rabi frequency to be absolutely huge compared to that. So I'm going to ignore inside, while I do this pi pulse, or pi over 2 pulse, the fact that I'm slightly off resonance. Okay? Otherwise, the torque vector is not exactly in the equator. Yeah?
So in the homework, we can assume the torque vector is in the equator.
That's right. That's going to need to be a hard pulse.
Okay.
So, let's say here it is, it's all along that axis. So I do this first pi over 2 pulse, and here I am. Okay? I'm in this state on the y-axis. Now what happens? So now I don't have, my laser's off, and I'm just sitting here for some amount of time t before I put on the second pi over 2 pulse. But my laser is detuned. This laser is the same as this one. So what happens to the Bloch vector in the rotating frame during this free evolution? It precesses. It precesses, even though there's no interaction, because I'm looking at the Bloch vector relative to my oscillator. My oscillator is oscillating at frequency omega L. In the lab frame, this thing is precessing at frequency omega EG. If they were the same, well then they would, nothing would happen. But because there's a difference between them, due to the detuning, the direction of the Bloch vector is precessing relative to my frequency. That's really important. Let's, for simplicity of drawing, because I'm so bad at drawing perspective, make this thing negative so that it precesses this direction. So goes the other way. I can't draw on the other side of the sphere. Okay? So, at this point, right here, the block vector is here, and it is processed by that phase. Okay? Now, I do the second pi over 2 pulse. What happens to this thing? I rotate again, right, by this axis, and it makes this angle with respect to the z-axis. Okay? So, the W component at this final time, after I'm done, is equal to cosine delta times t. If I was right on resonance, I'd go right to the North Pole. Okay? What is the probability to be in the excited state? One plus W over 2, which is 1 plus cos delta t over 2, which is like this. Okay. And the probability to be in the ground state is 1 minus that. Those are like the 2 ports of the interferometer. Exactly like the 2 ports of the interferometer. Now, importantly, at this stage, I have ignored the dephasing or any of the T1 or the T2 times. But let's just quickly put that in. Okay? So, if I were to say now, let's say this was a very fast pulse, I had a huge Rabi frequency that nothing happened during this guy. But now I'm leaving this on for this relatively long time. Well, what's going to happen is that this vector is going to shrink. It's going to decay towards the origin with a rate 1 over T2. And so this guy is going to be like that. And so this will be that. Or like this. And what that will mean in this case is my Ramsey fringes, and we call them that, they're like the interference fringes, will look just like this. With a decay time that is 1 over T2. So by measuring that decay of these Ramsey fringes, I can measure the T2 time, and that's how it's done. But there's one last thing. We don't have time, but I'll just mention here, we'll pick it up very quickly next lecture, which is inhomogeneous broadening. If I have inhomogeneous broadening, then the fringes are going to decay typically much more quickly than the actual T2 time that's intrinsic to the system. So I need to do something. And in fact, when I do, you may or may not have noticed a subtle difference here. Notice in this guy, I started in ground and came out in ground. Whereas here, I started in ground and came out in excited. So this is not, as stated, isomorphic to this. There's something different. And the thing that's different is the mirrors. I had the 2 pi over 2 pulses, which are like the beam splitters, but I forgot about the mirrors. The mirrors turn is like a pi pulse that flips ground and excited. So I put in a pi pulse in the middle here. That's like putting a mirror in between these mirrors. And that is what's known as a white light interferometer. Meaning it doesn't matter what the frequency is. As long as it's perfectly aligned, I'm going to get interference. And this is like a white light interferometer. It's known as you are studying your homework, a spin echo. And that's all the hints I'm going to give you for today. Yes?
Are there certain circumstances where the second pi over 2 pulse, I don't know what you want to call it, a minus pi over 2, or a rotation about the other axis?
Sure, I can do that as well. It's really a question, again, equivalently of how I set up these beam splitters. What's their coding? Are they symmetric beam splitters or not? Do I want the bright frame to come out here, or do I want it to come out there?
And doing that would have the effect of like switching the plus to the minus.
That's right,
minus to plus.
exactly. It's just a question of what the axis around which I rotate on the block sphere is encoded in how this 50-50 beam splitter is created.
And
So that,
are there like, but practically like in the lab, can you do that?
sure. Yeah. All right, very good. Good afternoon.